Hey everyone, welcome to this explainer. Today we're unpacking the physics of back and forth motion, and we're going to see how it silently rules the physical world all around us. Have you ever actually stopped to think about why things vibrate, swing, or bounce the way they do? Well, today we are tearing down this invisible engine of reality, oscillation, to show you exactly how it all works.
So let's start with a bit of a brain teaser. What do a playground swing, a high-tech MRI machine, and a collapsing bridge all actually have in common? I mean, on the surface, absolutely nothing. One's a kid's toy, one's a marvel of modern medicine, and the other, well, that's a catastrophic engineering failure. But beneath the surface, they are all governed by the exact same invisible engine, constant back and forth motion. We're going to explore how this motion impacts our world, sometimes beautifully saving lives, and other times, completely destroying solid steel.
All right, let's get right into it with Section 1, the rhythm of reality.
So whether we're talking about a microscopic vibrating atom or a giant grandfather clock, it all comes down to simple harmonic motion, or SHM for short. The crucial point here is that the further you pull an object away from its center, the harder it tries to snap back. Think of it like a really thick rubber band. The more aggressively you stretch it out of its comfortable resting state, the more aggressively it fights to return to normal, right? It just pulls super tight against your fingers. That proportional push and pull is the absolute foundation of everything we're looking at today.
Now, to make that constant motion happen, you literally only need 3 ingredients. Picture yourself on a playground swing. These 3 exact things are what keep you flying back and forth instead of just, dangling at the bottom. First, you have equilibrium, which is that dead center resting point. Then the restoring force. In this case, that's gravity constantly fighting to pull you back down to that center whenever you swing up into the air. And finally, inertia. That's the momentum you build up that causes you to wildly overshoot that bottom point and fly up the opposite side. So it's center, pull, overshoot, over and over again.
Moving right along to Section 2, anatomy of a bounce.
Okay, so these 4 simple terms let us completely map out the life cycle of a single bounce. Let's think about that playground swing once more. The amplitude is just how high you go, your absolute maximum stretch from the center. The time period is exactly how many seconds it takes you to swing all the way forward and then all the way back again. Now, frequency simply flips that around. It measures how many of those full back and forth cycles you manage to complete in a single second. And finally, angular frequency. That's just how physicists mathematically express how fast that whole cycle spins. With just these 4 basic terms, we can accurately describe everything from a bobbing spring to the sweeping motion of a massive skyscraper swaying in the wind.
Now this right here is super interesting because it illustrates why physicists use different mathematical phases depending purely on how the motion starts. Cosine represents pulling a swing as far back as it will go and then just dropping it from that dizzying maximum height. Sine, on the other hand, represents a totally different start. That's like sitting completely still at the bottom of the swing and having someone give you a massive shove to launch you outward. The resulting continuous back and forth motion? Identical. But we use a different phase mathematically, sine or cosine, just to account for how that physical journey actually began.
Which brings us to this elegant little piece of math. F equals negative kx. This is the defining equation of simple harmonic motion. And honestly, that negative sign just means the force is always stubbornly fighting against your movements. The F is the restoring force, the X is how far you're stretched, and the K is the stiffness of the whole system. Basically, if you pull to the right, the math dictates the force is going to pull to the left. Nature is basically playing the ultimate contrarian here.
Okay, Section 3, energy in constant motion.
Oscillation is really a masterclass in energy exchange. Think about that static dropping feeling at the absolute top of your swing arc, your extreme max stretch. You actually stop moving for a split second. Your velocity is 0 and your kinetic energy is 0. But your potential energy and your downward acceleration are totally maxed out, just begging to pull you back toward Earth. Then, as you rush through the dead center equilibrium, that completely flips. Boom, maximum speed and kinetic energy. It's this beautiful, seamless handoff between stored potential energy and explosive kinetic energy.
I want you to keep this number 4 in the back of your mind, because total energy depends on amplitude squared. If you pull a swing twice as high, you instantly get quadruple the total energy. A seemingly small change in physical height makes a massive, exponential difference in physics. To put that into perspective, it means a rumbling earthquake with double the shaking amplitude will actually hit a city with 4 times the destructive power. No way around it.
Next up, Section 4, real-world swings and springs.
Now, this formula reveals the ultimate secret behind a grandfather clock or a simple pendulum. The time it takes to swing relies exclusively on string length and gravity.
That T stands for the time period of one full swing, and it is entirely dictated by L, the length of the string being pulled by G, the constant of gravity. Picture the towering wooden case of an antique grandfather clock. The sheer physical length of the brass pendulum inside is exactly what dictates its ticking seconds.
And here is one of my absolute favorite facts. It is endlessly fascinating that whether you put a super light feather or a heavy bowling ball on that swing, it's going to keep the exact same rhythm. Because gravity acts on all mass equally, a heavy, dense weight actually doesn't swing any faster or slower than a light one. Well, provided you don't pull it back more than 15 degrees anyway.
But wait, what if we change this setup entirely? Unlike the swinging pendulum, if you hang a heavier weight on a bouncy spring, it will actually slow down the cycle. Meanwhile, a stiff, tightly coiled spring will speed it up. Think about the shock absorbers in your car. If you load up the trunk with really heavy luggage, the mass increases and your car's suspension bounces much slower. But if you install stiff, sports-tuned springs, that bounce gets dramatically faster and tighter.
Finally, we've arrived at Section 5, Friction, Force, and Resonance.
Welcome to the real messy world. We don't live in a frictionless vacuum, right? Without damped oscillation, a single pothole will leave your car's suspension bouncing up and down until the end of time. Damping is just when energy is constantly lost to the surroundings, like air friction or mechanical resistance. Shock absorbers are quite literally designed to damp the oscillation of your car's springs. They bleed off that kinetic energy as heat, so your car settles back down to a smooth, stable ride.
On the complete opposite side of damping, we have forced oscillation. Think of someone standing behind the playground swing and continuously pushing you at a set rhythm. That is a perfect example. The external force, the person pushing you, keeps the system moving, but you are no longer swinging purely on your own natural frequency. You are entirely bound to the rhythm of the driver pushing you.
But here is where things get wild. What happens when that external push flawlessly matches your system's own natural rhythm? That creates resonance. This precise matching of frequencies is a literal lifesaver. It's powerful enough to make an MRI machine work perfectly by resonating the atoms in your body to generate pristine medical images. But it is also terrifyingly destructive. If the wind perfectly matches the natural frequency of a solid steel suspension bridge, it will forcefully oscillate that structure higher and higher, sending a violent shudder through the metal until the bridge literally shakes itself to pieces and collapses. Resonance is a true superpower of nature.
So, if every object in reality has a natural frequency, what's yours? I want to leave you with that thought to remind you that from the microscopic atoms vibrating in your cells to the heavy steel suspension of the car you drive, oscillation is quite literally the heartbeat of reality. Every physical system has a rhythm it wants to follow. Understanding that rhythm gives us the power to build incredible technologies, map out energy, and prevent massive engineering disasters. So next time you see something bounce, vibrate, or swing, you'll know exactly what's powering it. Thanks for joining me on this explainer, and keep exploring the incredible mechanics of the world around you.